Hello everyone. In chapter 5, we're going to learn about the concept of probability, which is closely tied in with the concept of statistics, and it is going to help us determine a certain statistical phenomena that we would not be able to obtain without understanding probability. The first thing we need to understand, and what actually confuses a lot of people, is what is the difference between theoretical probability and experimental probability. Well, theoretical probability is utilized when you know the exact number of favorable outcomes of a procedure, as well as the total number of possible what we call simple outcomes of the procedure. When those two numbers are known, we can use theoretical probability to come up with the probability of the occurrence of an event without having to actually perform an experiment and see it. We can do it just using logic and reasoning, right? And so we just basically divide the number of favorable outcomes by the total number of possible outcomes. We get the probability. The simplest example, of course, being the rolling of the flipping of a fair coin, right? We have two possible outcomes, heads or tails. And if you want the probability of either of those two things happening, the probability that it's going to be heads is just going to be the number of favorable outcomes, which is 1, divided by the total number of outcomes, which is 2, right? So you get 1/2. The same would work with tails. We'll see that again in a minute. So remember, anytime the exact number of favorable outcomes and the total number of possible outcomes is known, we go with theoretical probability because it'll give us an exact value for the probability of the occurrence of an event. But oftentimes, especially in statistical applications, we don't know the precise number of favorable outcomes or the precise number of the all possible outcomes. So what we do is we basically depend on this form of probability, experimental probability. In this kind of probability, we basically run a procedure several times and then count the relative or calculate the relative frequency of the favorable outcome that we're observing and are interested in, and divide that by the total of number of times that we ran the procedure. So this is the difference between these two, and I wanted to clarify that before we proceed, because unfortunately most textbooks don't, and they just kind of introduce both notions, and students are thinking, well, why am I doing this? Why do we have to run through the simulation of coin flips when I know the probability should be this? Well, that's because they're just using that as a simulation for you because it's very easy to simulate. Otherwise, it's not necessary for a situation like the flipping of a coin or the rolling of a die to use experimental probability. But they provide fantastic examples which we can easily simulate for you. As it turns out, the more you run the procedure using experimental probability methods, the closer the result is going to get to what theoretical probability would have provided for you if you knew the exact number of favorable outcomes and the exact number of total possible outcomes. And as you run it an infinite number of times, in other words, as the number of times that you run it starts to approach infinity, the value of that you obtain using experimental probability will be exactly the value that theoretical probability would have provided for you to begin with. Okay, so the two merge once you run this particular version infinitely many times. First, we'll look at theoretical probability, which is the intuitive version you're probably most familiar with and you have encountered in your life. So it's very simple, remember, as we just said, to uh, compute this, as long as you know the total number of favorable simple outcomes and the exact total number of possible, again, simple outcomes. Uh, and let's suppose that a procedure has n equally likely outcomes. A simple event is an occurrence of any one of those equally likely outcomes, right? The probability of the occurrence of any of those simple events is just going to be 1 over n, because remember, those simple events, there's only one such simple event, right? So it'll just be the number of favorable outcomes for that event will be 1, and the total number of outcomes will be n, so 1 over n. Again, let's go back to our coin flip example. Think of the number of what are the equally likely outcomes? It could be heads or tails. So the total number of possible outcomes is 2. So if you want the probability that it's going to be heads, the number of favorable outcomes, well, that's only one of these two, right? So it's just going to be 1 on the top and divided by the total number of outcomes, which is 2. And do notice that it would be exactly the same for tails, right? The exact same probability would hold. And again, of course, we refer to this as theoretical probability because we didn't have to sit there and run through experiments, right? We only used our reasoning to come up with the result. So what is an event as opposed to a simple event? Well, first of all, simple events are themselves events as well. But what makes a regular non-simple event set apart is that it could be any collection of simple events. So it may be just one of those simple events or more than one, or it may even be all of the possible events that we're dealing with, and that can be called an event. Now, I will look at some examples. I'll make that very clear. So first of all, this set of all possible simple events or outcomes of a procedure is called a sample space of that procedure. A simple event is any subset of the sample space which contains only one element, right? In other words, one simple event in it. For our coin flip example, the sample space would be, normally we use the letter capital S, and we use set notation here. We just state all the possible simple outcomes separated by commas. So the sample space would just be HT, right? The simple events are the set containing only H and the set containing only T. Now consider rolling a fair die. This will be a better example so that we can actually describe some non-simple events for it as well. Non-simple events aren't that obvious for the coin flip. The only non-simple event you can really have here, which is not one of those, is what if you roll a die, flip a coin, and neither one of those results come. That's a possibility too. And of course, that probability is going to be 0 out of 2. So it'll be 0. But when it comes to rolling a fair die, we can come up with much nicer examples which are more intuitively satisfying. The sample space for that, of course, remember, a die has 6 sides. And if it's a fair die, when you roll it, any of those 6 numbers written on the 6 faces of the cube, which we call the die, should be possible as a result. And you can see that beautifully in this simulation that I located online. And as you can see, you have a number written on each side of this cube, which we call a die. And if it's a fair die, so one of the sides is not heavier or anything like that, when you roll it, any of the numbers may end up on the top. Like here we have 3, right? Here we would have 1, etc. So the sample space contains the numbers 1, 2, 3, 4, 5, 6, and the simple events would just be the set containing 1, the set containing 2, containing 3, 4, 5, and 6, right? Those would be the simple events. Notice that the number of events, simple events in the sample space here is 6. We call that the cardinality of the sample space. And we write n of s, that means the number of um, elements in the set S is 6, and the probability of the occurrence of each of these simple events which we discussed, it becoming the outcome being 1, 2, 3, all the way up to 6, is going to be 1 over 6, right? Because there's only going to be one such outcome out of 6 outcomes. So we say the probability of the outcome being 1, 2, 3, 4, 5, or 6 is going to be 1/6. Now, examples of non-simple events here would be something like this. Now, do notice normally they give the event to you in words, right? So just like here, and you will have to come up with the mathematical version yourself, the set which would describe that event. So here, in words, the event is the outcome is even. And of course, you can see that in this sample space, the even outcomes are 2, 4, 6, right? So there it is. There is the description of the same event using sets. And the probability of the event is just going to be basically the number of, items in the simple events in the event, which is going to be 3 simple events, divided by the total number of simple events, which as we know is 6, right? And of course, if we reduce it, we get 1/2. Now, sometimes, we can write that as represent that as a proportion. So we usually would, represent that using decimals. Some even use it as a percentage, so 50%. They all mean the same thing, of course. As another example of a non-simple event, what if the outcome, you're interested in the event that, this is a non-simple event because it doesn't have just one outcome, but what if you want the outcome to be prime? Well, remember that a prime number is a natural number larger than 1 whose only factors are 1 and itself. In other words, it's only divisible by 1 and itself, and it has to be larger than 1. So 1 is not prime because it's not larger than 1, it's equal to 1. So 2 is the first prime number here, then we have 3, and then we have 5. We skip 4 because it's divisible by 2, therefore not prime, because 2 is a number other than 1 or 4 itself. And we skip 6 because 6 is not prime given that it's divisible by 2 and 3, which are not 1 or itself. So the only 3 prime numbers here are 2, 3, and 5. So if we read this, we first will want to write the event in mathematical set form. So we say the set containing 2, 3, and 5. So the probability of what we're calling E2, event 2, is going to be the number of simple outcomes in it divided by the total number of simple outcomes. Again, it'll be 1/2. We could write it also as 0.5 or 50%. That's just completely, purely coincidental that these two happen to have the same number of elements. Now, here's another example of a non-simple event. What if we want the outcome to be greater than 4? So when we look at this set of all possible simple outcomes, we notice there are 2 simple outcomes whose value is greater than 4, and that would be 5 and 6. So in mathematical notation, we would write E3 equals the set containing 5 and 6, and the probability of that event E3 is just going to be the number of simple events in it divided by the total number of possible events, so it'll be 1/3, right? So do notice that, remember, we're dealing with relative frequencies basically here, right? So when you say the probability of 1 is 1/6, that means the relative frequency of the observation 1 will be 1/6 if you run this procedure infinitely many times, right? 1 On average, 1/6 of the time the result will be a 1. On average, on 1/6 of the time the result will be 2, etc., right? So uh, so the probability of the sample space, which is just going to be the sum of all those relative frequencies, should be what? Remember what the set of all relative frequencies of an event should equal to, or observation? They should equal to 1. And notice that's exactly what happens here. You can see how this is all tying in with the notion of relative frequency that we've already discussed. And this, of course, will be true for all sample spaces. Basically, you're saying what's the probability that the result will be either this or this or that or that or that or that, right? Of course, that's a certainty. So the probability is 1. So what if we said, what's the probability of the outcome being 7? Of course, there is no possible outcome of 7. So here you would say 0/6. So it would be 0. So notice that's the worst case scenario when it comes to probability. You're never going to have a negative probability. So probability lives somewhere between 0 and 1. 1 being certainty and 0 being impossibility. You can see what we just described beautifully in this graphic. So this describing probability. Notice that probabilities live between 0 and 1. So basically an impossible event would have a probability of 0. Any event in this zone down here would be a very unlikely event. Here we get to about a 50-50 chance or 0.5 probability. As you start moving to the certain zone, right? And remember, probability can only be at most 1, right? The probability of an event happening can't be more than 100% or 1, right? So the maximum possible probability value is 1. That's for certain events, right? That's why the probability of a sample space is 1, because, for example, when you roll a die, right, what's the probability that it's either going to be a 1 or a 2 or a 3 or a 4 or a 5 or a 6? Well, of course, the probability of one of those happening is going to be 100%. Or when you flip a coin, what's the probability that it's going to be heads or tails? See that compound probability, non-simple probability. Of course, it will be 1 as well, because it's definitely going to be either heads or tails. So remember, maximum possible probability value 1, minimum 0. All other probabilities somewhere between 0 and 1. Can't have any probability with less than 0 value, such as negative, or any probability greater than 1. So always keep that in mind. So when it comes to classic definition of probability, which is theoretical, that's before the set theoretic notation came in, before sets started kind of taking over all of mathematics and everything started being described in terms of sets. The definition was very simple. Suppose a procedure has n equally likely simple outcomes. Then if E is an event composed of m such simple outcomes, the probability of that event E is just going to be m over n. In other words, the probability of an event is the number of favorable simple outcomes divided by the total number of possible simple outcomes. The set theoretical definition of probability just brings sets in. Remember, suppose a procedure has sample space S, and remember that sample space is just a set containing all the possible simple events, equally likely simple events or outcomes, with cardinality n, meaning there is n of them, such possible simple outcomes. So we say n of S equals n. and let E be any subset of S with cardinality M, right? That is, n of E equals M. Then probability of the event E will be M over N. So this is everything that we've been discussing, just kind of like formalized. Here are some more examples to help us really understand this material. Let's consider the procedure involving two coin flips, right? So remember, the simple events here are not going to be just heads, tails, etc. So you have to consider what happens on one flip and then on the second flip, right? So the possible simple events here are going to be HH, in other words, heads on both flips, right? HT, first flip comes out heads, second flip comes out tails. And TH, the first one tails, second one heads, and finally two tails, right? So notice that the probability of HH or HT or TH or TT, all of them, they're all equally likely events, right? So the probability of each of them is 1/4. The sample space, of course, is the set containing all those simple events, right? So notice that the cardinality of the sample space will be 4. And what's the probability of the sample space? Well, basically 4 out of 4, so it's 1. Not surprising, right? The probability of the sample space is, is always 1. So here's an example of a non-simple event in this particular scenario. What if we are interested in the event that the outcomes of the two flips are different, right? Remember that that's going to include both of those simple events, right? So both of those simple events will comprise this one non-simple event. So the number or the cardinality of the event will be 2, and the probability of the event will be 2 out of 4, which is 1/2. So the probability, when you flip a coin twice, the probability that you're going to have different outcomes, right? One being head, the other being tail, is 1/2. How about a single birth, right? What are the possible simple outcomes? Well, it could be a boy or it could be a girl. So two simple outcomes. So the sample space will, of course, just contain those two items. The cardinality of the sample space will be 2, and the probability of the sample space will be 2/2, which is 1. Here's a non-simple event, right? What if neither B nor G comes out? Well, that's going to be impossible. So we say the event E is represented by the empty space, which we also call the null set. You can use this notation where you put two braces with nothing inside, or you can use the null set notation right there. So the probability of E is 0/2, which is E. Of course, remember, the probability of S itself is considered to be S itself, in other words, is a non-simple event. So the probability, what about the event that says the result is either heads or tails? Remember, that would be a non-simple event as well, and its probability will actually be 2/2, which is 1. So even though we have that here, this could belong to this column as well. What if we are looking at 3 births, right? What would be the possibility? Well, think about it. It could be all boys, 2 boys and a girl, but in order. See, in this case, order matters. These are called like permutations. So the order here matters, right? So 2B, in other words, first one is a boy, second one is a boy, third one is a girl, and then BGB, etc. So these are all the possible outcomes. We put them next to each other, with each other, into one set, and that becomes our sample space. And the number or the cardinality of the sample space is 8, and the probability of the sample space, as always, is 1. That's what always holds. Now, what about this non-simple event? What if you want to consider all three babies having the same sex. Notice that that event would comprise these two possible outcomes, right? This is supposed to be a comma here. For some reason, it became a period. Let me fix that. So that's a comma. You always separate them by commas. And notice that the cardinality of this event is 2. So the probability of the event will be 2 over the total number of outcomes, which is 8. That, remember, that's just the cardinality of the sample space. And we get 1 over 4 if we simplify that. And here are the outcomes for 3 coin flips. I put that here because I wanted you to see these are basically identical, okay? The only difference between these two is the letters, right? In one we're using B and G, in this one we're using head and tail, right? No difference. Everything about them is very similar. Here I looked at a different kind of non-simple event. What if we're interested in the outcome having 2 of the same kind of result, meaning either 2 heads or 2 tails. So notice that the outcomes that would satisfy that requirement would be HHT, HTH, THH, HTT, THT, and TTH, right? So notice that the number of such possibilities is 6 and the total number of outcomes is 8. So the probability of such an event occurring is 6 over 8 or 3/4. Make sure you study these carefully and absorb them before you move forward. It's all very simple, but it may be new for you, so spend some time with it. Pause the video, look at it, make sure it all makes sense to you. Now, coming up with these sample spaces for such procedures, like this one was the one for 3 births, right? It could be a little bit tricky, like as far as, oh, did I cover everything? There is a really beautiful way of handling these with graphics, and it's called a tree diagram. So here's where you start the procedure. Remember, this is going to be the first birth, right, that we're studying. So the first birth could result in a boy or a girl, right? Now, if that's a boy, then the result of the second birth, somehow I lost my B here. Let me put that in. No matter how much you try to get these perfect, there's always something that gets left out once you start presenting it. Okay, so now if the first result is a boy, then again the second result could be either a boy or a girl. Again, depending on which one, you're going to have another result for the third baby, etc. So one easy way, right, to determine all of these is what you just follow the tree, right? So you start here, you go boy, boy, boy. That's one possibility. Then you can go boy, boy, girl. You see, there's another possibility. Now you go down this one. So you go boy, girl, boy. You see that? This one. So you go boy, girl, girl. Or you can have girl, boy, boy, girl, boy, girl, and then girl, girl, boy, or girl, girl, girl. So using this tree diagram makes it very easy to come up with these sample spaces, okay? Here's another one for the 2 coin flips. Start the experiment. Here's the result of the first one. It's either going to be heads or tails. No matter which one, the next flip is going to have 2 possible outcomes, so either heads or tails or heads or tails. So just going down the tree, you see all the possible results. Heads on the first, heads on the second, HH. Or heads on the first, tails on the second, HT. Tail on the first, head on the second, heads on the second, tails on the first, tails on the second. So there it is. So these tree diagrams are really beautiful and very efficient. So now we will discuss what is meant by experimental probability. We've already hinted at it. Basically, the probability of an outcome from a random experiment is the relative frequency of the outcome if the experiment were run an infinite number of times. Again, that can be very confusing to people, and they were like, why would we want to do that if we can just do the number of favorable outcomes by the total number of outcomes? Remember, this is when you don't know the number of favorable outcomes or even the total number of possible outcomes. So basically, you control the situation. You run the experiment many times and then just keep a tally of how many times you get the favorable outcome. Then you just turn that into a relative frequency by dividing the number of times that the favorable outcome showed up by the total number of times that you ran the experiment, and you'll end up with the experimental probability of an event. Again, of course, you would only want to do this when you don't have those exact values for the favorable outcomes and the total number of outcomes. Now, the really important thing to understand is that if you have the time and resources to run the procedure infinitely many times, and if it's a procedure for which the number of favorable outcomes and the number of total possible outcomes may be available to you, then this probability, the experimental probability, will approach the theoretical probability value that you would have had. And in fact, once the number of runs become infinite, it becomes exactly the same value you would have obtained using theoretical probability. We will do an experiment now for both coin flips and dies on StatCrunch to show you what we mean here, and to it's very interesting how it works out. Okay, so let's go ahead and go to StatCrunch. We're going to click on applets, and then we're going to simulation. We'll start with coin flipping, and of course we're going to set the probability to be 0.5. That means it's a fair coin with heads and tails have an equal probability. Now we're going to tally the heads in tosses, and we want the number, count the times where the number is 1. And let's go ahead and compute. So now we can just go through one run. So notice we did one run, and in the simulation it turned out to be heads, tails, so the number of heads was 0. So the proportion is 0 out of 1. Now let's do 5 more runs for a total of 6 runs. It's right there, see? So right now, basically we're at 33% of the runs resulting in heads, right? Now let's run through 1,000 more runs. Now you see what's happening. The more you do this, the more the experimental result is going to approach the theoretical result. We know that if we run it an infinite number of times, half the time we should get what? If the coin is fair, we expect to get heads half of the time. And notice how the proportion is starting to approach a half. So out of a total of 1,006 runs, 497 in this simulation, which basically just flips the coin for you, has come up as heads. So now if you just keep going, sometimes this is going to go up, it's going to go down a little bit, but the larger the number of runs becomes, it will eventually start stabilizing exactly at 1/2 or 0.5. See, you go to 0.505 right here. Now we can go 1,000 more runs. You see, sometimes it goes up a little bit. Right there, it's going up. But as you do this, eventually, notice I'm going through it quickly now. Notice every time I click this, I'm adding 1,000 more runs, right? So eventually, when you go to you get to really significant numbers of runs, right? It will eventually start stabilizing very close to 0.50, or basically 0.5, right? So now, of course, again, even there you'll see some fluctuations, but less and less, right? Now it's becoming very stable toward the relative frequency out of the total number of runs is getting really, really stuck at 0.5, right? Very close to 0.5. And you can run through this, it's quite fun, and you can see how what we expect to be true, in fact, is true, okay? So this was for, this is already at 70,006 runs. That's not even all that many. Now, you can actually see the data very nicely here. These are the number of runs as opposed to which result. And notice how this is the relative frequency or the proportion graph, right? What proportion of those runs were heads, right? Notice the proportion of runs that were heads is approaching exactly 0.5, okay? So that's a really nice way of running through a lot of experiments without actually having to sit there and flip coins, right? So now let's take a look at the other applet, which does a rolling of a dice, right? So here, let's see what proportion of the time the result it lands on. Say it doesn't matter which one you pick. Let's just say it lands on 1. Makes no difference, because it could land on 1, 2, 3, 4, 5, or 6, right? So let's actually bring the calculator for a second. Now we know the probability, that the theoretical probability is 1/6, right? So if we run the experiment an infinite number of times, meaning roll a die, we expect to get the result 1/6 of the time, right? Which is right there, 0.1, and then the 6 keeps repeating, right? So let's see what happens here when we do these runs, okay? So let's just go through one run. That just means I'm going to roll the die one time, right? Notice the value came up 6. So the value I'm interested in, which is what? 1, didn't come up. That's why 0 over 1 gives us what? 0. Now let's do 5 more runs, right? In other words, let's roll the die 5 more times, right? So notice, out of 6 times that we've rolled it, none of them has come up on a 1, right? Now let's do 1,000 runs. Okay, very, very interesting, right? So now you see, as you do the number of runs more and more often, see, now you're getting close to the result. Let's see, let's go back to our calculator. You see, we're approaching that 0.16 bar, right? Which means 1.6 with the 6 repeating. See, 0.168. So now as you start adding more and more runs, you're in fact going to start getting really close to that 0.166666, right? Notice right now, to get this, all you're doing is dividing the number of favorable outcomes by the total number of times that you've run this experiment, right? So you see, you're going to have some fluctuations. In some runs you'll go up, down, but if you start to approach infinity, remember this is just 7,000 runs, right? To get to that exact 0.166666 forever, 1/6 in other words, you would want to run infinitely many times, which of course we don't have time for, but it's not going to take all that many times. Notice every time I'm hitting this button here, I'm running through 1,000 rolls of a die, right? So, but if you just keep going a few hundred, even if you get to 70, 80,000 runs, you start getting pretty close to the number that you're looking for, which is that 0.1666 already, 43,000 runs, right? So, and this is only going to get better and better. And in fact, once your number of runs reaches infinity, it'll be exactly 1/6, as you would expect. All right, so that's a great simulation for understanding what we mean by practical, or experimental probability. All right, so again, to summarize our understanding of experimental property as utilized in statistics, the probability of an outcome from a random experiment is the relative frequency of the outcome if the experiment were run an infinite number of times. So here's one which should be very simple for you right now. We're rolling a 6-sided die. We want to know the probability of rolling a 4. You should be able to answer this, so pause the video, see if you can answer it, and then come back. All right, so if you recall, the sample space here is the set containing the results 1, 2, 3, 4, 5, and 6, right? The particular event we're interested in here is a simple event, and it basically would like the result to be 4. So notice that the probability of the event E is going to be the number of E, in other words, the cardinality of that set E that which we created here, divided by the cardinality of the sample space, right? So it's going to be 1/6. Now, we know what that means from the standpoint of theoretical probability, right? But from the standpoint of experimental probability, it means if you were to roll a die a very large number of times, you would expect the outcome to be 4 approximately 1/6 of the time, right? Now, the situation becomes much more interesting if you roll a pair of dice, such that is done in Las Vegas, etc. Now, interestingly enough, of course, just to give you a little bit of historical background, the entire discipline of probability basically was created by a large number of mathematicians in Europe, which happened to many of them in France, which happened to also be interested in gambling. So probability is inseparable from gambling. A lot of the best examples that we use in probability are actually examples from gambling scenarios. So here is a pair of fair dice which is rolled, and we want to know these sum probabilities. We want the sum of the numbers on the two faces of the two dice to be these possibilities, which are shown here in blue, right? So most students they get confused with this at first, because, for example, when you ask them what's the probability of getting a 5, right, they just go, okay, 1 and 4 and 2 and 3, they both give you 5, so there's 2 of those, and the total number of sums, as you can see here, is you can have 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because we know 1 is impossible, of course, right? But so 2 out of 11, right? Well, that's completely wrong, and that's because what they're not realizing is that, yes, the first die may be a 1 and the second die may be a 2, or actually, since we were talking about 5, let's say the first die may be 1 and the result of the second die may be 3 to give you 5, but that's a different roll than the first die being 3 and the second one being 2. So when you think of the possibility of 2 and 3 adding to give you 5 for the sum of the numbers on the two dice, you have to consider that 2, 3 is a different roll from 3, 2. You just have to label one of the dice in your mind or color it differently as dice number one, die number one, and the second one as die number two. Again, you can color it a different color or whatever to keep track of it, and there'll be different results. So starting here with the probability of 1, of course, you know, there's no way the sum of the two numbers on the two dice can be 1. That's the the smallest possible sum is if they're both 1s, which is 2. So this one is just going to be 0. Notice that the total number of possible outcomes in here is going to be 36, right? There's 6 times 6, so this table has 36 values in it, right? So 36 possible simple outcomes, right? Of course, this is the outcome 1, 1, right? This is the outcome 1, 2. This is the outcome 1, 3, right? So you could write them as ordered pairs to keep track of them like this. So you would say this is like the outcome 1, 1, right? This would be the outcome 1, 2. That means the first die comes up 1, the second comes up 2. This would be 1, 3, etc., right? So what is the probability that a 2 is going to come up? Let me erase all that to make this easier to see. We can see there's only one way to get a 2, right? So that's just going to be 1 out of a total of how many? 36, right? Now, how many ways are there of we can get a 3 to come up? Notice there's 2 ways. This table is beautiful because it really summarizes it for you nicely. So here, this looks like 56. It's actually 36. So 2 out of 36, right? Which is 1 over 18. So you always want to give the answer in the simplest form, right? What about the probability of getting a 4? Notice there are 3 ways of getting a 4. 1 here, 3 there, 2, and 3 here, 1 there. Okay, so 3 over 36, that'll be 1 over 12. The probability of getting a 5, there's 1, 2, 3, 4 ways of getting 5. So 4 over 36, which is the same as 1/9. Probability of getting a 6, there's 1, 2, 3, 4, 5 ways a 6 can come up. So it's 5 over 36. That's not reducible any further. Now, you can see from the table, you know how in craps this is the favorite number because that is the most likely outcome, right? So 7s, the probability of getting a 7 is going to be, notice, 1, 2, 3, 4, 5, 6 again. So 6 over 36, which is 1/6. That is the most probable roll when you roll a pair of dice, right? So in the long run, you would expect to get a total of 7 when you roll pairs of dice 1/6 of the time. If you run the experiment many times, right? P of 8, so in here, notice we have 2, 4, 5 again, so 5 out of 36. Probability of a 9, that's going to be 4 out of 36, right? Which is 1 over 9. P of 10, that's going to be 3 over 36, which is 1 over 12. And P of 11, that's going to be 2 out of 36 possible outcomes, so 1 over 18. P of 12, that's, notice 2 and 12 are the least likely outcomes, right? So that's also going to be 1 out of 36. All right. And of course, this is how they determine the odds, etc., for when you go to somewhere like Las Vegas. So we already mentioned the fact that the sample space of a random experiment is the group of all possible outcomes. An event is some of the outcomes, all of them, or none of them, right? In other words, any subset of the sample space. So you're going, how can none of them be a subset of that? Because remember, when you write the, say, for example, a simple set like let's just look at this simple set 1 2, right? So what are all the possible subsets of that? Remember, you can have the subset containing only 1, you can have the subset containing only 2, you can have a subset containing both 1 and 2. In other words, yes, every set is a subset of itself as well. Or you can have the subset that doesn't contain either one. This last one, the empty set, is super significant because it's a subset of every sample space. This is where some probabilities will end up being 0, right? When you're in that zone. All right. Again, here we just go over the same thing we discussed before, that the probability of an event is just going to be the cardinality of the event, which is m. Let's say there are m simple events in the event, and n is the cardinality of the sample space, or the number of simple events in the sample space, and you do that division to get your probability. So here's an example. A group of 10 students in one of the author's algebra classes were broken up in such a way that 2 were nursing majors, 4 were business majors. I like to keep track of facts like that in kind of a more graphic, visual way. So I'm just going to write, just start keeping track of that, right? 2 are nursing majors, so I'm just going to put n equals 2. 4 were business majors, so I'm going to put b equals 4. Much of the taming of a word problem comes from organizing your information, because information in a word problem is all over the place. So you want to make sure that you organize it and make some sense out of it, right? And 3 were on the, 1 was I think they meant architecture, but I mean, at least in my days, we used to call that major architecture, but I didn't want to touch that out of respect for the author. I left it. So let's just go with a equals 1, and 3 were undecided. So u equals 3, right? Now, also what I like to do, as soon as I do something like that, I like to get a total and make sure that it makes sense. Remember, there were 10 students. This should add up to 10. 4, 7, 8, 10, which is indeed the case, right? All right. So find P of n. In other words, what's the probability that if you pick a random student, you just close your eyes and you put your name on one of the names of these students, what's the probability that that student is going to be a nursing major, right? And of course, that's just going to be the number for the nursing major divided by the number for the entire sample space. So it's going to be, notice n is 2, right? So we're going to get 2 over n of s. Again, most of this you should be able to do without watching me do it. So for your own sake, when you see, oh, I got this, right? Stop the video, pause it, go do it, and then come and compare our answers. That's the most effective way to learn math, all right? And of course, that's going to reduce to 1/5, right? Construct a frequency and relative frequency table of the students' majors. Find P of B, P of A, and P of U. So let's go ahead and look at those tables together. There are some more parts to this problem. We're going to find P of philosophy and find the probability of randomly selecting a nursing, business, architecture, or undecided major. Notice that basically means P of the sample space. because those are the only majors there, right? Why does that make sense? We'll look at that together. So we already talked about this, right? 1/5, 2 over 10, or zero point 0.2 being the probability of being a nursing major. The frequency and relative frequency table are very easy to construct. Notice we know there's 2 nursing, 4 in business, 1 in architecture, and 3 in undecided, for a total of 10. The relative frequencies are just going to be 2 over the total number 10, 4 over 10, 1 over 10, and 3 over 10. Notice what happens when you add those. You get 2, 6, 7, 10 out of 10, which is 1, as you would expect. Why does it make sense? Because you're adding relative frequencies, right? So now you can clearly see how the relative frequency and the probability are basically the same. So there are 2 ways you can express the fact that there are 2 nursing students. You can say the relative frequency of nursing majors in that group of 10 students is 2 out of 10, right? Or you can specify it as a probability in this way. You say, if you were to randomly select the student out of these 10 students, what's the probability that that student will be a nursing major? You see how the 2 phrasings are different, but the outcome is the same. So remember, a probability is a form of a relative frequency. So from the far right column of the table, notice that P of B, which is business, is just going to be 4/10, so which is 0.4. P of undecided is just going to be 3/10, right? Now, they wanted P of philosophy. There are no philosophy majors here, right? So that's just going to be 0 out of 10 results. So therefore, the probability of one of them being a philosophy major is 0. And also notice that the relative frequency of philosophy majors in this group is also 0, right? Now, in the part where they ask you calculate the relative frequency of the nursing, business, architecture, or undecided students, well, remember, that's the entire sample space, and that always ends up being 10 over 10, right? So look, if you just add all those relative frequencies, what do you get? 1. This goes back to that beautiful graphic we discussed about, we discussed earlier, with the the bottom showing the impossible events at 0 probability, the top showing a certain event at probability of 1. So they call it a sure event here, or certain, the same thing. Probability of any event is basically going to be between 0 and 1, inclusive, meaning it could be 0 or it could be 1 as well. And the sum of all the probabilities of the basically the simple events, right, is always going to be 1. All right, so if you remember, pie charts also give us relative frequencies, right? They do it a little bit differently than frequency tables, because they use percentages, right? But remember, percentages are easily convertible to either fractions or decimals, right? So when they ask us, we can use a pie chart to determine probabilities. Here's a pie chart that describes the percentages of 1,445 online adults who use various numbers of social media websites, right? Find the probability that a person randomly selected from the survey uses exactly 3 sites, right? So you come over here, you look at where the 3 sites is, right? And you can see it's 12%. So we're going to describe it as 12%. Remember, that's 12 over 100, which is 0.12. If they wanted you to give the answer as a fraction, you would reduce that, right? We know 4 goes into 12 3 times, and it goes into 125 times, right? So you would give this result, right? But here, usually they're just going to ask you to leave it in decimal form, okay? Just like with relative frequencies. At least 3 sites, right? Now, that's going to be different because that's going to include the probability for the, or the relative frequency or the percentage for 3 sites, 4 sites, and 5 sites, right? So basically, we're going to add all those. So 12 and 5 is 17 and 2 is 19. Again, if you think you've got this, pause the video, do it, and then come back and compare your answers. So 19% or 0.19, right? Or 19 over 100. At most 3 sites, right? That means less than or equal to 3 sites. So that means you want to count the 3s, the 2s, the 1s, and the nones, right? So you add all those, 22 to 36, that's 48, 68, 71, 81, 83. So basically 83%, right? Which is 0.83. And that's how you would handle a situation like that. Actually, when I look at these two down here, it looks like I'm short because these two are 7. That would have been an easier way to do it anyway, right? If we just calculate the ones that are more than 3 and then take away what? Take away from, take that away from 100%. So I think I miscounted these. It should be 93%. Of course, if I'm, say, doing, for instance, a test, I would always check these on a calculator, as you should, because we're all human and we can make mistakes. So let's correct that. All right, so we need to change this to 93%. Again, if you want to know at most 3 sites, right, that means all but these two, right? So the easiest way is just to combine those two. That's 7%. What's that from 100%? 93%. But some of those should give you the same thing. I think I just added them wrong in my head. Let me go ahead and use a calculator real quickly. So we are going to be adding, oh, I didn't want that. Let me bring this over here. So we're going to be adding, okay, I don't know what I did over here. Let's go to home. Okay, there we go. All right, so we're going to combine 22 with 36 with 23 and 12, and we do get 93. Okay, so I just misadded. All right, always double check. Notice I caught it because first of all I noticed the fact that, oh, there's only 7 here, that can't be 83. And secondly, because I always would check these on a calculator just to be on the safe side anyway. From inspecting the pie chart, the student concludes that 36% of all Americans use just one site, right? Well, what would you tell the students? Remember, no matter how good the data, collecting methods may have been, the sample population would always be different from the total population, at least by a margin of error, right? Also notice here they surveyed online adults. So not only will that be that margin of error, but this survey would not be representative of all adult Americans anyway, given the fact that they haven't surveyed any people who don't even go online. That would give a very different result, right? All right, so what is called a random variable? It's a numerical measure of an outcome from a random experiment. We often use a capital letter for it to stand for a random variable. Let's look at an example of how it is utilized. For example, now, let's say we roll a six-sided die. You know how loosely we've been just saying P of 4, right? What's the probability that a 4 is going to come up? Well, if you really want to be theoretically correct or mathematically precise, you would write P of x equals 4. Again, we usually, if it's an equal situation, we usually don't even use the x. We just say P of 4. But it's very useful because what if I want to say what is the probability that the outcome is going to be less than or equal to 4, right? Or greater than 4, etc., right? So, or between 3 and 6 inclusive, including 3 and 6, right? So let's see if we can handle these kind of quickly. So remember, we're rolling a six-sided die, so our sample space here would include 1, 2, 3, 4, 5, or 6, right? So what's the probability that x is 4? Notice there's only one possible value, 1, 4, so out of 6. So that's just 1, 6. What is so for part 1, the event we're looking at only has one element in it, which is 4. So now we want to know what's the probability that x is less than or equal to 4. So the event we're looking at contains which of these simple outcomes? Well, 1, 2, 3, and 4, because less than or equal to 4. So 1, 2, 3, or 4. Those would be the outcomes in this non-simple event, right? So the probability is going to be the number of the event or the cardinality of the event divided by the cardinality of the sample space, right? So it's going to be 4 over 6, which we can simplify to 2/3, right? What if x is greater than 4? The probability that the outcome of the event, random experiment is greater than 4. Notice that that event is going to contain, if you don't want to get confused, you can call these different events, like event 1, event 2, event 3. So here you would have event 1, event 2 actually here. All right. So event 3 would have the outputs. Remember, this is strictly greater than 4. So 5 and 6 would be the only such numbers, right? So here we would say this would be the number of E3, meaning the cardinality of E3 divided by the cardinality of the sample space, which would be 2 over 6, which is 1/3. What is the probability that the outcome of the random experiment will be between 3 and 6? Let's see. So let's call that event 4. What would be the simple events that are contained in event 4? Well, it says inclusive, less than, so x is greater than or equal to 3, but less than or equal to 6, right? So that's going to include both 3 and 6. So possible values in that event would be 3, 4, 5, or 6, right? So this is going to be the cardinality of E4, event 4, divided by the cardinality of the sample space. So the cardinality of E4 is 4 divided by the cardinality of the sample space, which is 6. So we get 2/3. All right, so very simple, but you just have to basically know the definitions and what they mean. There should be no problem. The last thing we want to cover in this set before we look at some practice exercises from the 5.1 homework set is interpreting the area of a bar of a density histogram. There is a really interesting connection between those and probability. And remember that when you look at a density histogram, it's not the height of the bar that tells you the relative frequency of the given class. It's the area of the bar. Remember? And remember, if the area of the bar is the relative frequency, that means it's also the what? I think I heard you say probability, right? In that case, you're right. So basically, the proportion of the observations that lie in the bar's class will be the probability. And the probability of randomly selecting an observation that lies in the bar's class will give us that. Now, let's go look at a really nice example we've already looked at. All right, so here we have a nice density histogram for rolling a pair of fair dice, right? So notice that the outcomes can be any number from 2 to 3 to 4 to 5, right? All the way to 12. Something between 2 and 12, right? Could be the outcome of the rolling of a pair of dice, right? Now, we did this before. Remember on this page, let me remind you, right here from here, and remember we worked all these out. So I have moved them to the other page, so we'll go see them again there. Now, if you recall, the probability of rolling a 2 was just 1 out of 36 because there's only one way you can get a 2, a 1, and a 1, right? For 3, it was 2 out of 36. Remember, 1 and 2, and 2 and 1. For 4, it was 3 out of 36. For 5, it was 4 out of 36, all the way up to the max frequency at for 7, which was 6 over 36, and then they went down again like this. Very beautiful symmetric situation we have here, right? For the rolling of a pair of dice. Now, do notice that those values are basically the areas of each of those bars, right? Because the probability is the same as the relative frequency, and what's represented by the area of each bar in a density histogram, the relative frequency, so therefore also the probability, right? So this is why some people call these probability density graphs, right? So notice that the probability of the sample space would be the probability that the outcome is going to be 2, 3, 4, 5, 6, all the way up to 12, right? And notice, of course, if we add all those fractions, we better get what? 1, right? And we do. So there it is. So probability is a really, really beautiful field of study. We all can connect to it because we all have played a game or two in our lives. So now we will go and take a look at some of the homework problems to make sure you can handle all of them. All right, so here's a problem that deals with that coin flipping simulation which we did together earlier. And notice that they have shown you the results in this graphic here. Okay, so let's read it first. The simulations of flipping a coin 5 times and then an additional 10,000 times are shown in the figures. Determine the first 5 outcomes of the simulated experiment. What was the relative frequency of heads after 5 flips of the coin? Is this a good estimate of the probability of getting heads from flipping a coin once? What was the relative frequency of heads after 10,005 flips of the coin? Is that a good estimate for the probability of getting heads from flipping a coin once? So when we look at this graphic right here, remember, this is showing you the proportion of times, right, out of the number of runs that the result was heads, right? Notice over here, we've gone, the relative frequency was 1. What does that mean? That means 1 out of 1 time it was heads. That means the result of the first flip was heads, right? But notice there's a dip, right? So that means the relative frequency has gone from 1 to 0.5, right? How can that happen? That means out of 2 runs, right, 1 of them was only heads, right? So that means the second outcome was tails. Does that make sense? Because look, what is the relative frequency here? That's 0.5, right? So how can the relative frequency of the coin turning up heads after two flips become 0.5? That's if only one of the two was heads. Now again, a dip. Now the relative frequency after three flips is 0.3 or so, right? That means what? 1/3. So now what? So that means this must have also been what? That's showing another dip. So therefore the third flip also came up what? Tails. Again it goes down, and again it goes down. So in other words, only the first flip had resulted in heads. So here's we're looking at this situation. The first one was heads, the rest were all tails, and that's because this relative frequency is going down. You have to really try to understand this graph. It's not showing you the frequency, it's showing you the relative frequency, right? And the relative frequency can only go down consistently is if each subsequent run is giving you the opposite of the outcome that you are interested in. Now, so now look. So after after the 5 runs, the proportion was 2. Is that a good estimate for what you expect the probability of just one flip to be? Of course not. We know what the probability should be. It should be 0.5. So you cannot depend on a few short runs to determine the probability of an event. Now look at what happens here when we do an additional 10,000 runs, right? For a total of 10,005. Now the relative frequency has become 0.4961. And notice how it is approaching what? 0.5. So is this a better estimate? Absolutely. Okay, of what the probability of one flip should be. Okay, so that's what we are talking about here. Why is it good? Because it's very close to what we expected to be, 0.5. All right. So here a student guesses the answer for a true or false test question. What's the probability that the student guesses the correct answer? Of course, when it's a true or false question, there are only a total of 2 possible outcomes, and only one of them is favorable, right, to getting it correct. So this would be what? 1 out of 2. Now, if this were multiple choice with 4 choices, right, and only one of them is correct, let's say B, right? So what's the probability that they corrected the correct answer if they completely guessed, they had no idea? Well, it would be 1 outcome out of how many? 4. So this would go down. This is 0.5 and this is 0.25. Now if this were even more options, the chances of getting it right by guessing would have gone down and the probability would have been even lower. All right, so let's go for a ride to Vegas. We have a roulette table, and you know how you have, the reds, right? So notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Of course, take 1 through 36, divide it into 2, you get 18. So 18 reds, 18 blacks, and then this is the reason the house always wins, because you don't just have those two, do you? Otherwise, this would have probably been the best probability, and I think it still is one of the better odds of winning in Vegas anyway. But so when you pick red or black, you don't exactly have a 1/2 probability of getting it right, because there's these two that throw things off, right? So the probability of getting a 12, however, right? So some people would incorrectly say it's what? They would say it is 1 out of 36, right? That would be the correct answer. It's actually 1 out of what? Notice there's 16 items, the outcomes there, 16 there. I'm sorry, 18. So 18 there. 1 second, let me fix those. So we have 18 outcomes there, 18 there for a total of 36, and then 2 here for a total of what? 38. So the probability of any one of those numbers on the top there, or actually any of these scenarios, would be 1 out of 38. All right, so here we're looking at a spinner question. Someone spins the spinner shown in this figure. Find the probability that it's going to land or stop on a 3 here. So the way you want to approach these is very simple. You want to make sure that you break the circle up into an equal number of parts. Which parts? The smaller parts. So for example, here you'll want to make sure that you are breaking it up into, let's see, let's break it up like this, and we're just gonna do so. All right, so notice right now it's broken up into 1, 2, 3, 4 times 2, so 8 equal parts, right? So of those 8 equal parts, right, how many does 3 represent? Well, notice 3 represents 2 of those 8 equal parts. So the probability of 3 is going to be 2 out of 8, right? So that's going to be, if you reduce it, you get 1/4, right? Now, notice if they had asked us for the probability of another number, it would have been different. For example, what if we wanted to know what's the probability that it'll land in 4, right? Notice 4 is composed of 1, 2, 3, 4 of those equal parts. So out of how many? 8. So that would have been 4 over 8, which is 1/2. Okay? These offer us excellent opportunities to practice probability. These spinners. So here they're giving you a different kind of die. They're giving you a 12-sided die, right? So you want to know the probability that the outcome is going to be 7 when you roll it, right? So remember, since it's you don't want to be in autopilot mode and go, oh, it's a die, so it's going to be 1/6. No, this is a 12-sided die. So the probability of any it landing on any one of those 12 numbers is going to be 1 out of 12, or 1/12. So be careful with those. Okay, in this one, the students in a statistics class were surveyed about the number of hours they worked per week. The density histogram shown describes their responses. For a randomly selected student in the class, let X be the number of hours this student works per week. And that's how we're defining the variable here. And we want to know what's the probability of X greater than or equal to 15. That means we want to know the probability that the student worked more than 15 hours, right? Notice there are 2 ways we can do that, right? We can either add this, 4 values, right? Easier would have been if we just start with 1 and take away those 2, right? So we can just go 1 minus 0.11 minus 0.31. All right, I'm not going to put my calculator abilities to the test again. I'm just going to use our device here. So now we're just going to do 1 minus, if this decides to write, minus 0.11 minus 0.31. Okay, that's where we get our 0.58. What's the probability that the number of hours worked was less than 25, right? So that means all of those, right? Again, we could sit here and add all those, or less than 25 just means, remember, they all add up to 1, right? So you could just do 1 minus take away those. So that'll be the easiest way. So you'll just go 1 minus 2 times 0.13, basically, right? That's where we get that. Of course, remember, you could have done 0.31. You could have added all of those. That would have worked too, right? Because that would be less than 25. So 0.31 plus 0.11 plus 0.13 plus 0.19, right? And we get the same answer, of course. It's just more efficient to do it the other way. The probability that the number of hours worked was between 20 and 30, right? So here you're just going to be adding those two probabilities, right? So 0.19 plus 0.13. Okay. Now, if you ever want to quickly check to see if this is a correct probability distribution table, you would just add all those, make sure they add to what? To 1. So describe the shape of the distribution. Notice it looks like there's a peak here and there's a peak here. So this would be a bimodal. Rather than use the mean or the median to estimate, let me get rid of this one. To estimate the center of the entire population, explain why it would be more meaningful to separate the data. Because we always do that with bimodal. That's always the best thing to do with bimodals, because it'll make more sense. Because there's usually a reason why it breaks up into two different mounds, right? Okay, so that's that. All right, so here's one of those where you need to recall the empirical rule which we discussed in chapter 4. Let me remind you of that rule. Remember that if you have a unimodal distribution that's also symmetric, and you have the mean right there in the center, of course, you know, with such distributions, the mean, median, and mode are all the same value. Then if you go one standard deviation to the right or left, in other words, within one standard deviation of the mean, you capture 68% of the observations. If you go two standard deviations to either right or left, within that zone, you'll capture 95% of the observations. And if you go two standard deviations away, right, you will capture, sorry, we already said that, three standard deviations away, you will capture 99.7%. Basically all of the data, almost, right? Except for a few outliers, right? Now, so when we go to this question, it says a total of 940 healthy pregnant women between 20 and 34 years of age inclusive participated in a study. The distribution of their lengths of pregnancy is unimodal and symmetric, with a mean of 279.3 days and a standard deviation of 8.3 days. Estimate the probability that a woman randomly selected from the study had a pregnancy that lasted between 263 and 296 days. Now, the best thing for us to do in a scenario like this is go ahead and take the mean, which is in this case 279.3 days, add 8.3, which is one standard deviation to it, and also subtract this one standard deviation to it. This will give us the 68% group, right? So basically, if we take care of that calculation, so we have my bad. Let me move this calculator over here. So we have all right, so 279.3, actually, let's go back and put the point in there, minus 8.3. So you get 271. Now let's go ahead and add it. So I'm just going to be lazy and copy it, and then just change that minus to a plus. Okay, so we get 287.6. So these are going to be the group within one standard deviation, right? So what we call the region, which is x bar minus standard deviation, comma, x bar plus one standard deviation, right? Which, as we know, comprises around 68%, right? So now what we will do is we will go ahead and compute what two standard deviations away would result in. So we're going to be looking at x bar minus 2s, right? The interval from x bar minus 2s to x bar plus 2s, right? And then we'll also, this will capture, as you know, around 95% of the population, or the, I mean, not population, sorry, the observations in this group or sample. And then x bar minus 3s and x bar plus 3s, right? So I'm going to do most of it on the calculator now that you know how it's done. All right, so if we're efficient with the calculator, we can actually save a lot of time. So I'm going to copy this, right? And remember, I'm just going to multiply the standard deviation here by 2, right? So let me go ahead and click in here. All right, so that's minus 2 times 8.3. So that'll be the lower bound for that 95% group. So that's 262.7. Now for the upper bound, we're going to do x bar plus 2s. So we're just going to take the, actually, let me just take that and change that minus to a plus. All right, so we're going plus 2 standard deviations now. So we get 295.9. Now for the last one, we're going to do all that again, except we're going to do it with 3s. So in here, so basically I'm going to copy that and I'm going to change that 2 to 3. Different calculators do this differently, but I just happen to use this nice HP calculator today. So 254.4, I like to mix it up for you so you can see different possibilities. 254.4, not parentheses, comma. Now we're going to do the upper bound for the 99.7% group. So we're going just to take that and we will change that minus to a plus. All right, so 304.2. Let's go 304.2, correct? All right, so remember, this is going to be where 99.7% of all observations will be. All right, so now let's get rid of the calculator. We don't need that anymore. So now we can answer any question they want. So they say the probability that a woman randomly selected had a pregnancy that lasted between 263 and 296. Does that look familiar? Basically, they want this group, right? So you know it's going to be the 95% probability, right? But do keep in mind that you can write this as 0.95. Now I realize they've put some decimal there. More than 0.95, they put something in the thousandths place, but you know what, you're not going to need to. If you just type in 0.95, that'll be acceptable, okay? So you can just, instead of that 0.954, you can put, now of course remember these are going to be, these values are slightly higher than these, right? That's why it's safe to put something slightly more than 0.95, right? So but even 0.95 in here would have worked. The probability that a woman randomly selected from the study had a pregnancy that lasted between 254 and 304. You see that here? It's the 99.7% group. So remember, you can write that in decimal form as 0.997. That's where that comes from. And this one is the probability that it's between 271 and 288. Recognize that right there. Okay, so this one is going to be the 68% group. And remember, for this one, again, if you just type in 0.68, it'll be acceptable as a correct answer. That's it. So basically that should get you through this assignment. As always, remember that you can see me in office hours, Monday, Tuesday, Wednesday, 12 to 1. It's in your syllabus and in several announcements, the Zoom link. Or you can also see me, you know, on Sunday when we do our summary of events, all right, the week's lessons. So stay safe and till the next video.